My name is Ruman Mahmood, and this is my lab report for Lab 4 Circuits. The purpose of this lab is to apply principles of energy and current conservation in order to predict the behavior of circuits when containing different components such as resistors, and to then check our predictions through measuring current and potential differences along the circuit. The fundamental physics principles being used in this lab are the conservation of energy and charge, Kirchhoff's circuit laws, these being the node rule and loop rule, Ohm's law, and the equation for capacitance. For the results, the current in the 2-resistor circuit was calculated to be 0.02 amps, and the RC was calculated to be 6 seconds. The model of the experiment includes batteries, ammeters, resistors, capacitors, and bulbs, arranged in the ways described to attain the desired circuit. The assumptions made for the lab are that the resistance of the wires and ammeters are negligible and that the EMF equals V1 minus V2. For the system and surroundings of the experiment, the system is the circuit while the surroundings are everything else. For the first part of the experiment, we are asked to make a simple series circuit with two 1.5 volt batteries, two resistors with the stated values, and two ammeters. The predictions of the results are stated as the resistance and voltage are found through adding the given numbers, and then the current is found through dividing those given numbers. If the connection to the ammeter was reversed, the current would still read 0.02 amps. We are then asked to use the same circuit, but replace an ammeter with a voltmeter, and through this, it can be found that the voltmeter reads 3 volts while the ammeter reads 0 amps, as the circuit is open, so there is no current, and the potential difference along the opening is equal to that of the battery. The voltmeter was then used to measure the potential difference for each part of the path around the circuit, and through this, these values were obtained. 3 volts were gained from the batteries, 0.96 volts were lost from the 47 ohm resistor, and 2.04 volts were lost from the 100 ohm resistor. This result supports the loop rule as the change in voltage was 0. The reading of the ammeter does not change as the voltmeter has a high resistance, so no current flows through it, thus not affecting it. This is an extension of the graph that was given in the instructions, which graphs potential versus position around the circuit. Now we were meant to replace the voltmeter with an ammeter in parallel with the 100 ohm resistor. The experimental value was 0.02 amps, but the actual value should have read 0.06 amps as the 100 ohm resistor experiences less current due to a split at the node when the circuit is in parallel. Due to the ammeter having no resistance, the equivalent resistance of the parallel portion of the circuit decreases, thus increasing the current due to Ohm's law. From the potential difference measurements from earlier, these are the values of resistance from these elements of the circuit. Now, for the second part of the experiment, we were meant to create a circuit consisting of a 10 ohm bulb, a 9 volt battery, and a 200 millifarad capacitor in a series. The batteries are connected to the bulb and capacitor in series, and the bulb was observed to initially be bright but then go out. Then the battery was disconnected and the bulb was connected directly to the capacitor, in which the same behavior was observed. We were then to measure the time it takes in seconds for the capacitor to charge using the two bulbs. For the 10 ohm bulb, it took 10.7 seconds to charge and 12.5 seconds to discharge, while for the 20 ohm bulb, it took 17.6 seconds to charge and 22.4 seconds to discharge. Now here we have a similar setup, although we are using a 30 ohm bulb, 9 volt battery, and 200 millifarad capacitor set up in series. The V was recorded every 2 seconds for 20 seconds, so ln of V over V naught could be plotted. From the graph data, the slope is equal to -1 divided by RC, which was then calculated to be 5.64 seconds. This is similar to the true RC, which was 6 seconds. Possible sources of error in this experiment were human error, as there could be discrepancies when measuring the stopwatch versus the capacitor discharging. Along with this, it's possible that the equipment did not act ideally and ended up having a resistance which would affect the current. Discrepancies with the model are that the model created wasn't ideal and therefore wouldn't act as a flawless simulation. For the first discussion question, it asks what would be different about using a simulated and real ammeter, and the answer is that the real ammeter would have resistance and would therefore lower the current. For the second question, it asks what is different between the use of a real battery and capacitor as opposed to ideal ones. In this case, the ideal capacitor would charge instantly with no resistance to slow the current, However, in real life, there is resistance, which results in a slower charging time for the capacitor. The conclusions of this lab are that we learn to create circuits, measure voltage, and use these principles to calculate values in a circuit.